Hello, everybody, and welcome to this stream by me, the one who role plays a software developer on the internet, the perfect Darjan. So, before we start, just give me 1 second. Yeah, I can hear myself. No, I'm not a narcissist. Is as you may know, in the last few streams, we have had some problems with the audio catching up. So yes, it's a good thing. It has absolutely caught up. Pray the Omnisaya. So let's start. What do we have for today? So I'm quite excited. If you were here yesterday, you know why. But let me show you. Basically, the majority of the issues that we raised in terms of features enhancements for the LZSS-like compressor are resolved. In order to finish the basic framework for that compressor, we only need two things. They are so related to each other that we have a single card, which is to implement a byte-oriented decoder. For this card, we're going to write that decoder. Obviously, we're going to test it, etc., and test the documentation. And then we're going to add as an example to the compressor, basically the same thing that we did for the compressor, for the byte-oriented encoder back in the day, where we created an example of a compressor. We're going to create an example of a decompressor, and that means that we will have a library and two binaries, yes, as an examples, as a pair of examples, but we will have a library and two binaries, one that does compression, the other that does decompression, working each other, compressing from a file to a file. So basically, we would have achieved our first goal, which was to implement decompression. Have we finished? No, by a long margin. So there are a few things that I want to add into the future. I'm not going to add in as cards at the moment, but let's think about uplifting the crate, the Rust crate, into a workspace. That workspace having two crates, one for the library and a second crate with proper binaries for the compressor and the compressor. Those compressors, the compressors having, for example, the ability to parse command line arguments. So to work not only on standard input and standard output. Other things that I don't want to forget is to refactor the decompressor that we wrote yesterday. Reason why the code is more or less readable, I think is not very elegant. And lastly, optimization, both in terms of optimizing the compressor. For that, we will take a look at new tooling that we have not used yet about profiling a Rust application, etc. And obviously to optimize the decoder encoder. So at the moment we're using a byte-oriented decoder, which is the easiest one to write ever. But I will show you by taking a look at the dump of the symbols, which remember we have an example dedicated to that, that the symbols that the compressor outputs, part of it can be further compressed. And if you have seen, I think I have not uploaded it yet. I have not uploaded yet as a video, but if you watched a couple of streams ago, I made a short presentation on compression, and I already said that basically the compressor, when it creates symbols, it can further compress part of those symbols, typically the lengths. So those are things that I want to do in the future. However, given that this is a big milestone, it's just having our first version of the library complete with examples, etc. And the fact that I am not streaming for 3 days. My next stream will be next Wednesday. On Wednesday, I want to start a completely new project. So not continue with LZSS, not even continuing compression. I want to completely shift around and do another thing. That's basically for two reasons: the Hawthorne effect, so the fact that changes increase attention, increase productivity, and give us a new perspective on things. Secondly, I want the code to rot a little. Okay, right now the code is fresh in my mind. I can read it. That doesn't mean that the code is elegant or well refactored. It's just I know it like the back of my hand. I can read it. If I give it a pause, if I shift to another project, then when I come back, I will find code that I cannot read, I cannot understand immediately, even if it works, but it can take me a couple of minutes to understand what I was thinking about and have a different perspective on refactoring the code, especially for the decoder. This is the best I can do, given that I don't have the advantage of pair programming. I know if you are a professional developer, you may be having a laugh at me. Yes, that holy grail of having pair programming, having two people looking at the same code, right? Fancy that. It doesn't happen often. Obviously, in professional coding, it doesn't happen because companies don't want to pay two developers to have one writing code that they're just looking at it and yapping and pointing at the monitor. And for solo developers, because we are solo, right? We don't have a pair, so we cannot do that. All right, so I don't know what project I'm going to choose for Wednesday. That's why I have not changed the schedule on here on Twitch. But I can assure you, on Wednesday we're going to start a different project. I hope that's going to be as interesting for you or more than it is going to be for me. But I promise, after today, when we finish this, we are not over about compression, something that I love a lot. I think that even this compressor has still some future in terms of having more updates, having more upgrades, more enhancements, etc. So we will come back to it. But today, once again, we're just going to basically tie a little bow and have our first version up and running. Okay, so let me change things around. All right, so I already created the card. I already created the card in the dashboard, put it here. I have already created a branch, which, by the way, this is something I forgot yesterday. I basically created the compressor by resuscitating the branch of the mock decoder. So it took me a few minutes to get Git things all back in line. So today I didn't forget. I have just created a branch for our byte-oriented decoder. And let's open Kate. No, compare Kate. There we are. So as we did with the mock decoder, which was written in the same module as the encoder, we're going to do the same for the fixed byte coder. Okay, so we're going to basically we're going to create our decoder, and we're going to implement the decode trait for that decoder in the same module. So first thing first, not giving me error message. Now it does. The trait is unknown. The bar is not known. That is absolutely correct. Another thing that I plan to do, by the way, is to do a re-export so that the traits appear directly at the grade level. I think that makes sense because especially the encode trait, the encode module has basically nothing other than the definition of the trait itself. All right, so in order to write the decoder, we're going to take a look at the mock decoder first. So for the mock decoder, what did we need? Well, for the decoder, we needed a reader. That is still true. But now, like we did with the encoder, our reader is actually going to be an object that implements the read trait. And of course, because we are receiving it with a mutable reference, we're going to need a lifetime for it. And of course, as soon as I do this, the read trait is unknown. So let's add it up. All right, so what's the next thing we do that we need? Here it says the input position. We are not going to need this for this decoder because we're using a reader. So the reader is always has a position. So I don't think we need this. We don't need a configuration as is. However, as you remember, we still need at least one parameter. So the same way as we did with the mock decoder that didn't need the full configuration, but we copied the constructor way to work on the configuration object from the encoder to make it more easy to pair the encoder to the decoder. So we're going to do the same. Basically, what I mean by that is that it's going to give us reader, and then it's read, of course, and then it's going to have these three parameters. It needs to have bytes for length and bytes for distance. Okay, so basically everything that was here. Oops, not there. Not here. Literal length floor. I'm not sure with this. Yes, we need it because that is actually what the function is called, right? Output buffer size. I know that's the maximum, not the floor. No, I don't think we need this. All right, so we're going to keep it like that. We will see if we need to add more things. We're going to use the same one here. COF, what's for length, what's for distance. There we have it. So we have the basic decoder, and now we need to implement the decode tray. The decode tray needs these three methods. So need COF is simple as always. Get output buffer size. Remember, this is the maximum length for a literal block. So the maximum length of a literal block. And here we have something quite interesting indeed, is that while batch for length is known and literal length floor is known, the SAF is not the decoder, is the encoder. Okay, so we're going to use part of the encoder for the decoder, and that is the main reason I want to have the encoder and the decoder in the same module, because I can do that. Okay, thanks again. Anyways, I want to do that because yes, this allows me to reuse code, which makes sense. That needs to be reused because they are using the same mechanism, right? They are both fixed size, byte-oriented encoder and decoder. That and also the decoder is there to decode what the encoder did. So they are literal there. Now, the difference is here. The literal length floor that is removed from here. So I'm going to add it back. So this can be calculated. Perfect. So now the last thing that we need to do is to properly decode a symbol. So how do we do that? Well, the first thing that we need to read from our input is enough bytes for the length, because remember that the length contains both the binary flag to say if the symbol is a literal block or a reference. So we're going to take that. Now, because this is going to happen for every single symbol, and optional, we may also need to read the distance, we're also going to do something like what happened here. Okay, we're going to have the same internal buffer, and we're going to build it exactly the same way. So once again, proving why having the encoder and the decoder both in the same module is very helpful. All right, so now that we have an internal buffer, reading the next symbol is the first step is quite obvious. We just need to get the reader with exact the internal buffer, but only to read the length. Are incorrect? Oh, you're absolutely correct. All right. Now, symbol. Yes. The symbol that is part of the decoder. Let me check that we don't use it in the test now. Yeah, okay. So now that we have read this, first thing we need to do, of course, is the first byte. Sorry, the first byte. If the most significant bit of the first byte of the buffer is not 0, let's take a look at the write reference. Sorry, write literal. Write length. Where do I have write length? Oi. Write length. Wait, didn't be sure. Write length has the symbol flag max. Oh, sorry. When we are writing when we're writing a literal, we are setting up the mask. When we're writing a reference, the mask is 0. So when the mask is not 0, is a literal or an end of file. Okay, so this is literal or end of file. How do we know which one is it? and that's obvious, is first of all, if we need EOF. Okay, this is important. If we need EOF, so first of all, let's well, we need to calculate the actual length. So first of all, so let's remove the flag, and then well, in fact, let's have the row length to be equal to, let's see what type to be equal to this. Let's write some code that can be read. Okay, so we're reading. We are calculating if what we have is a literal or in the file, and it doesn't matter how. We also need to need a row length. We're going to do that obviously through a method. Okay, and it's important to know that here we don't care about the mask. We're going to let this method to get rid of the mask if it exists. Okay, so once that we have that, then if is literal or EOF, sorry, if it's a literal or EOF, then if the decoder has been configured to needs EOF and the row length is equal to 0, then that's the definition of the EOF symbol. So we return EOF. If that's not the case, then the real length is going to be the row length plus the literal length floor, right? So when we need EOF, literal length floor is 1. When we don't need EOF is 0. So a 0 when we don't need EOF is actually a real length of 1. Now that we have this length calculated, then basically we need to copy the literal block here, right? So first of all, we're going to add an assert here that the real length is enough for the output buffer. In fact, we should do is to put the decompressor here, but not with the length. But with the size of the buffer as it should have been configured. That way we don't need to do the test here. It is already known to be true. So now the only thing that we need to do is to do a self-reader with the exact of the output buffer only until the real length. And if that works, you will return the symbol literal with the length. To let the user know how many bytes of the output buffer were actually used. So now we have these two branches completely covered, which is the reference. So for the reference, we are going to read for the rest of the internal buffer. Until the end. And then we're going to call we're going to adjust the distance in another function of the decoding of the distance. We're going to split it up into two methods. One that is just going to basically do the same as the decode row length does, only that this one so I'm thinking about it. This and this method, the code distance, are basically the same. They're going to read bytes and put them, accumulate them into a number. This one needs to remove a mask. This doesn't, but then it needs to adjust the distance. So can we write these two methods in a different way? Yes, we're just going to decode the distance and use a common method to accumulate numbers, and that's all. So decode distance. This one. And no, this one and this one can say. So one that we have the row length and the distance, obviously the only thing that we need to return is a reference with the distance, so with the length being adjusted. And distance. Oh, don't need immutable here. Let me see. So let's do, okay, so this implementation, which is that we need to do. I'm going to create a function that adjusts reference length, another that adjusts the literal length. Okay, adjust literal length is basically this one. But I think I'm going to do something better. I'm going to add a little bit of logic here. So we're going to just literal length. And what it's going to do is that in this case, it's going to return, and in the other case, it's going to return the actual length. Why am I doing that? Because now all this code about here, I'm going to rewrite it again. Is simply, I'm going to match the result of adjusted literal length of the more length course. And in the case that we have a none, we return the OF. And in the case that we have now real length, you just need to use. And I think the code is a little bit more clear. So we're going to adjust the literal length or we could just compose no, I'm missing something. I'm missing this if. Yes, all of this. This much is what goes here. Let's write it. Yes, equal literal length Okay. And instead, what we're going to do is to have everything in a single method. So we're going to just call matchself decode literal length. That's going to give us everything. So the first is to calculate the row length. And the row length is going to be to decode assigned value. No, is endian value. The internal buffer, but only for the length. And we're going to mask the output with a mask that we're going to create. It is kind of static mask. EEF. That way I don't need to write on the internal buffer, set it here. What is called mask literal. So this is what we want to eight times batch for length. That's why you have parentheses. You see. Okay, so now we have a row length, and now if we add here the code for the adjust, we call literal length, returns, yeah. So now there, and because of that, we're going to make this into a function. And I don't like this because that depends on a lot of things. Right, so I think the code is becoming more readable as we speak. So now we are reading the length part, and then if the first byte is flagging that it is a literal VOF, then we decode it as potentially literal length. If instead we get a none, then that's directly end of file. If not, then we get a length. We read those bytes directly into the output buffer, so we avoid a double copy of the data, and we return the symbol. If not, we read the distance, we decode the distance, and instead of that, just let's call it the code, the code, code, the code, the code. And we don't have row length here, as we should there. All right, so what's the problem now? Parameter there, the code literal length, right? So let's take a look at it from the top down. In order to read the next symbol, we need that the output buffer I don't know why we want that way. The actual output buffer has a minimum length of what we may need to read. If it is a literal, then we're going to read this. Let's make it a function. Right, let's make everything a function so the code is easy to read. Read length bytes. Right, so in order to read the next symbol, we have an assert to test things. We read the length bytes. And then we check if the first byte of what we have read is a literal or end of file. If it is, then we decode the literal length. If the result is known, we don't have a literal length, so it's an end of file. If we do, we read that block. I think doesn't make sense to create a function with read literal block because I think the context is very clear, and we return that. And if not, we're going to create. What is happening here? Implicit returns. we are going to create read distance bytes, which is this. So now to make the output be balanced, we do this. All right. So our reference by decoding the reference length and decoding the distance. And this is very well balanced, but we need to write in those two methods. Before that, the code literal length is missing one function, which is called be value. And this one receives just one slice, and the output is a size. So this is actually a class method. And you guys should prefer to use, well, here bits. So the maximum value that we can decode, right, depends on bits, right? If our use sizes are 64 bits and the slice length has to be less or equal than 64 divided by 8, and the same for when we have 32 bits use sizes, 32 divided by 8, 4, the slice has to be less or equal to 8, sorry, 4 bytes. By the way, this kind of creates an incompatibility, a fundamental incompatibility, when you compile this application in 32 bits and 64 bits architecture. So you cannot compress on one architecture and decode in the second one. That's not going to work very well. But we will deal with that. I'm going to forget about that. And this is a bug. Choose 64 architectures size. Mostly in info code. All right, so this is a bug. We're going to add it. The dashboard is there. Let's create the issue. And let's keep it here in the background. Because, it's not something that we need to do at the moment. All right, so how do we decode VE value? We have now result which is equal to 0. And then for each of the bytes in slice, the result is changed to the result shifted 8 with an O to the byte. And lastly, so as the value. So what's happening here? This is size. This is your U32. What's happening? And this byte size. What's happening? Oh, that was the actual problem. All right, so now the issue here is the argument is incorrect. It's correct. Okay, so now we have the code literal length, and as I was saying before, we're missing two functions. One to decode the reference length, which now, of course, doesn't need an option. It's a number by itself. So row length is the same. We don't need to mask. And the only thing that we need to do is to return the row length plus the break-even length. Now the break-even length, we don't have it. Okay, but we can calculate it from the encoder. There. So now that's the decode reference length. And the last thing that we need is to decode the distance. code distance, which is this and as well. And I know what you're thinking about. Is here we're passing the buffer. That in read distance bytes, it is also calculated, and in read length bytes is also calculated. So we have that a little bit repeated all over the place. But I think Rust is very fast calculating these things. It's just doing pointer arithmetic, if I remember correctly. And the issue would be that a single read length bytes leads to two different implementations of the decode. We're going to keep it like that. The code distance, I have just created it. Oh, I have duplicated. There it is. Read distance bytes. No, it's not this. Oh, yeah, I know. Okay, so that's basically the code. Bytes for distance is not used at all. Yes, it is. It is. Oh, it is used here twice. That is no longer used anywhere. Interesting. So we're going to keep it like that. Come on. You told me that there is not used 204. Oh, yes, this is not 4, so I need to be construct. Okay, so now what we need to do is to add the documentation, to add the tests, and with that we finish the decoder itself. So once that is done, we just need to create our decompressor example. That uses this decoder. But we will do that after we go and take a little pause to stretch and for hydration. Let me add a little bit of music for the stream. That being said, if you are on YouTube, music is off. Anyways, I will see you in 2 minutes. And we're back. So let me remove the wrong bit. This one. Oh, I see. Put this in the wrong place. There. So let's continue. And as I was saying, the next thing that we need is the boring thing, which is documentation. Luckily, this is going to be extra easy because we just need to document the new method. The struct itself, this decoder reads Osimo of bytes, length include symbol flag, take the exact number, typo, birth of bytes to code. This is also take some number of bytes to code. So we have the struct there and creates a new instance of a coder. This the coder uses bytes for names, bytes to encode both. So the code of the symbol type the reference and the set. We call keep track of this URL, which changes the behavior. It doesn't change here the behavior. You can change the behavior of next symbol, what can be decoded. So now we have this. All the methods are private, and this is an implementation of a trait. So this is documented in the trait itself. So easy peasy, we have documented our decoder. Let's take a look. So for the fixed byte coder, now we have two structs. We have a new struct, which is a decoder. The decoder has implementation, implements a method called new, and it has a treated implementation of the decode trait, which links here, where the three methods are documented too. I can see that the documentation copied the documentation of the trait, which is brilliant. And we're good to go for the documentation. So the last part is the tests. So for the test, we could test quite a lot, to be honest, even though technically the only function to test is next symbol. Do we want to do that or test later with the little things? I think that by testing the edge cases of next symbol, we can test all those quote unquote little things. So let's go ahead and test next symbol. Right, so the first thing that we're going to need is to create a decoder. For that to work, we need a reader. Which is going to be a vector because vectors implement the reader trait. What else do we need? I need COF. This is something that we need to test. So we're going to have some decoders with list to true, other to false. Bytes for length and bytes for distance. Bytes for length, I'm going to use 1. Bytes for distance, I'm going to use once at the moment for this test, at least. Which test? So we're going to have an output buffer that is going to be large enough. Okay. Yeah, in the vector should implement read. Doesn't the vector implement read? It always has. Like if I did a test in the old implementation. Oh, no, I did not. I did not, in fact. So that's going to be interesting. I think I use a slice. Yes. So that's important because that means that for each of the tests that need to change the input buffer, We need to create a new decoder. It is what it is. But it's a pity that it doesn't let you use the vector directly. Instead, you need to go through a slice variable, but whatever. Anyways, what do we want to test first? First thing is read length bytes. Read length bytes just reads enough bytes for length, which is 1. So we're going to make it equal to 0. Why? Because then, no, 0, sorry. In the mask. Okay, I'm going to make it equal to the mask for literal. Why? Because then the result of decoding this should be if decoding the next symbol should be EOF. Okay, this breaks because we cannot do inequality on the results, blah, 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 blah. So we're going to assert instead that index symbol is okay. And furthermore, that symbol is symbol equal path. Right? No, we can't pick the reference. Oh, because we're sending a reference. What's happening? Oh, this is the only one that that didn't change to be mutable. Okay. Test fails. Let's do step by step. Panicked. Mhm. 284. Okay. So it is going this way. And it's trying to read some bytes, which is wrong. So we have a problem. We indeed have a big problem. Because, so this is right. It went through the correct arm of the if. I have a mask on. Bytes is actually the mask. Let me see if I can. Yeah. To make it even more explicit. Right. This is the mask, and it is just the mask, just a zero. So this works. And now decode literal length. Is trying to decode the BE value. We should have, oh, for freak's sake, the mask is wrong. So let me show you the problem. I'm getting the result of getting the number, so 0x80. And what I wanted to do is to mask only the part that is just the length. So if I'm going to change the name of the parameter to make it more explicit, what I want to do is to mask a length. And you know what? The length is completely the opposite of this mask. Which, if I remember correctly, I don't. Mask. Yes. Something important is that unlike in C, in the C language, and I think C++ too, probably even Java, there are two negations, so logical negation and bitwise negation. Rust only has one. Rust only has one negation, which is the bitwise for numbers. And for booleans, it is actually the logical Boolean negation. The reasoning is that, unlike in C, you need to convert a number to a Boolean. You cannot just use a number as a Boolean. And you can actually see that in place in my implementation of is literal or UF. In C, I only need to write this part. But in Rust, I need to add this part so it can become a Boolean. So I think that I have solved the mask problem, and I was right. So, boys and girls and in-betweens, that's why we do tests. It looked very silly and turned out to be an error. All right, so that is for end of file true. Now, the same symbol means a completely different thing if we don't have end of files. Let's test that. And now this assert can be put all together as we had before. Edge case literal. So with the same input, we are going to now have a decoder that doesn't accept end of file symbols. So now the same is going to mean a literal containing A. So we don't need to create the buffer again. We can reuse the same buffer. So the next symbol is going to be an okay. The symbol now is actually going to be a literal one. And furthermore, buffer, or the first byte of the buffer, is going to be that A that we put there. Yeah, excuse me. Let's see if that's correct, and say that it is not correct. And in fact, there is a panic because the length of the buffer is not enough. what? And then the output buffer has a length of get output buffer size. Oh, absolutely correct. Problem being, we need a larger buffer for false than for true. So we're going to swap out the tests. And obviously we need to swap out the assertions. And our books. Beautiful. So those are edge cases, important ones, because we start with the exact first byte. For the rest, I mean, the maximum symbol is interesting. Well, actually, we have another edge case with a minimum literal. And that is when is the minimum literal, but now with needs EOF. So the value is actually different. It's a 1 because with a 0, it is end of file. This test is still okay. So those are the edge cases for literals and minimums. Edge cases for maximum. In this case, obviously, is when we have the maximum number invisible. But now that means that the buffer, not the buffer, our input buffer or vector needs to have enough data for that. So we're going to extend with an slice of this and we're going to overboard. It's not needed, but that way we can make it into a constant. It can be expressed like that when we do it correctly, of course. Was the right, so we're going to extend with a lot of piece after the A. And yeah, and we are going to create a decoder. And then we're going to connect symbol of that buffer. The result should be the maximum literal that can happen. Of course, the first value of the buffer will be the A. The second one should be a B. And this references the last one should also be a B. Perfect. And now let's redo that when we don't need EOF. So this vector is large enough. Now change that. And it should be the same. The difference is that the get output buffer size is going to differ from one to the other. We're going to assume that this is correct because this is actually a copy of a function from the encoder, so we need this to be correct. Yeah. So we have now tested the edge cases for end of file and literal blocks. So now for references, now here we're going to make a different trick. Obviously, we need to change we're going to change things. So now we have just a 0, with 0 means minimum length for the reference. But now we also need distance. And we're going to have Excuse me. So what we're going to do, in order to also test the the get v value, the decode v value function, we're going to have distances of 2 bytes. Okay, so you could reader, we create a decoder. In this case, we don't care if this is true or false, but we want our distances to have 2 bytes. And now we are not going to do it this way because we need a lot of things to test. So first, we're going to assert, yeah, we have an OK. We're going to unwrap it. And then we're going to insert equal that no, we don't need to do that. What we need to do is if let symbol reference of length distance is equal to s, which should not equal. No? All right. So in this case, we're going to assert at the length is equal to the minimum length, which is the break-even length. Then we're going to assert that the distance is going to be big endian, so this at the top, this on the bottom, plus 1 because of the displacement of distances. This is the decoder. Oh, freak. So with that, we have tested that the function to decode bytes is actually coding multiple bytes in the right order, and that with a length of 0, we get a reference of the minimum length. So do we need an edge case for a max reference? Not really, right? Because the maximum distance is going to be the maximum distance, which is this plus the value here. The mask is okay, so I don't think we need it. Okay, so now we have the tests, we have the documentation. So it's time to stage and commit. Fixed size byte oriented decoder. All right, so that solves in theory this card, but as I was saying, we're going to make an example. Oof. Hey. And we may need this, but at the moment, this is what we have. Okay, so first of all, we need a handle for stdin. And return color. Okay, this decoder needs a reader. So standard info. And then needs COF byte for length, byte for distance, which we're going to copy directly from the compressor. So the compressor and the compressor can work with each other. In this case, we don't have all of these methods. The only one that we have is literal length. Okay, and then we're going to create the compressor. The decompressor doesn't need anything else. So we're just going to read. Sorry, we don't need to read the input. We just need to decompress, because this is going to decompress calling next symbol of the decoder. and the decoder is going to be reading from standard input. Right? Yes, the compress has a parameter to whether we decompress only a certain amount of bytes or everything. That works when we have end of files here. And lastly, for the decompressor, we have a get buffer. And this one, we're going to have a write-up. Okay, so I think that this should decompress a compressed file that was compressed by the compressor, and it should work. So first of all, we are going to run the compressor from, let's say, the license file to a test. It's called compress, no compress. And now for the decompress, we're going to take that test output and decompress it. If all goes fine, the license and test original should be the same. It is not. That's a bummer. We have a bug. Almost at the end. That's a shame. Version is missing the last symbol, I think, which is a literal column space. Let's check that out with the encoder dump that we're going to configure exactly like the encoder. So reference lengths from 3 to 130. This distance is 655, x6, and literal length of 127. Here it says that the end is a reference. That's funny. because it doesn't make sense. So this is the end of file. That's easy to know. But it says that before that, there's a reference of 6245. Is this 245? Yes, it is. F0 is 240 plus 4, 244 plus 1 because this is 245, 0. And this is a length of a raw length of 3 plus 3 for break-even 6. So this encoder dump is providing the same N in theory as the compressor with the same configuration. At least the two last symbols seem to be the same. The decompressor, however, gets shown for only, and that's more worrisome, for only 2 bytes, not for the last symbol or what in theory is the last symbol. Let's run this one, which is the back-to-back compressor and the compressor with mock symbols. Yep. As you can see, there's a problem. Yeah, there is a problem. And the problem is, I think, in the compressor. And I'm pretty sure I know where the problem is going to be. In the compressor, when we call flush, here is where we have the problem. So what is the difference between the compress method and the flush method? The compress method doesn't finish to compress everything, right? It's going to compress only until the block to match doesn't have the maximum size. For the tail end, we need to call flush, right? And because as you can see here, the condition is that the length is long enough. Here it just until Ceph now reaches the end of the buffer. However, what happens if we reach the end of the buffer and we were accumulating a literal? And that is the bug. That's a bug that we didn't have before, because before I wasn't checking this. I probably was checking with MD or something like that, that finishes with a reference, but it doesn't happen here. So what we need to do is to, okay, this, something like this. However, this gets very hard to test here. But we should have a test about that. So what happens is, if pending literals is some, so we are accumulating something, this is the last opportunity we have to flush pending literals. And that is the problem. That's the bug here. Check it out. Problem solved. Now the encoder dump says that after the last reference there was a literal with 2 bytes, which is what we were missing. And now our decompress is still wrong. What the what? Oh yes, because we need to run the compress first. Because it was not probably in the compressor. Okay, issue solved. So that's worrisome, especially once again because I will need to figure out how to create a test for this that is short enough to be a workable test. Okay, so the compressor, the difference is a typo and the resolution of the bug. And encoder dump and encode the code, we just have change the configurations. Let me show. So they work like the other compressor. So what I'm going to do, I'm going to create 2 commits, one just with this. Fix flash take in internet consideration. Hey, hello. So I don't know why my mic was muted. Sorry about that. And I don't even know for how long it has been muted. Probably since the last time I sneezed. I'm sorry, I need to be more present about those things. Anyways, if you have been patient enough to watch the stream, if you're watching the VOD in YouTube, you are my hero because with no background music, no mic, it was just something moving on the screen. So thank you if you are still watching there. Anyways, as I was saying at the beginning of this stream, now we have a library that works. We have examples of a compressor and decompressor. So I want to make a pause, to take a pause on this project. When we come back, we will solve this bug. We will do other things such as optimization, refactoring, changing the cargo project to be a workspace. So it will have the library plus propers, compressor and decompressor applications, with command line arguments, etc., etc. That will be when we come back to this project. My next stream is next Wednesday, and there we're going to start with a new project. I have not decided yet, so I have not put anything in the Twitch schedule, and probably I will leave it as a surprise until I start on Wednesday. But I hope it will be as exciting as it is for me to start a new project, learn different things about Rust. And other than that, I think today has been absolutely a great day. So thank you very much, everybody, for joining me here on Twitch or for watching the VOD on Twitch or on YouTube. This has been The Perfect Dargen, signing off.